Students, welcome once again in the class of topology. In the previous videos, we have started the topic of compact spaces, and in today's class, we will not move on to the difficult, typical theorems, lemmas, etc. In fact, we are going to have some examples. We are having some very easy concepts relating to compact spaces, and that will be the foundation stone for you to study further topics of compact spaces. So here I am going to start with very easy concepts of compact spaces. So the first one is, it is the theorem, you can say the exercise, you can say the question. Prove that indiscrete topological space is always compact. So this is the first result we are going to prove that today, that the indiscrete topological space is always a compact space. A proof is very easy. Why? Because if X, and I am denoting by I the indiscrete topology, so let Xi be the indiscrete topological space. We know that in indiscrete topology we are having only two members. One is the phi, other is the set X itself. So there are only two open sets. So if we will talk about an open cover of the space X, then the open cover will contain only one set, because there are only two sets. So only one set will be there, that is X itself, which will form the open cover for the set X. So the singleton set X is the only open cover of X. It is the only open cover, and it contains only one member, so it itself is a finite subcover of itself. And to prove it a compact space, what else we need? We need only a finite subcover. And the set itself, if I denote it by C, then C itself is a finite subcover of itself, because it contains only one member. So that means the indiscrete topological space is a compact space, because it has only one open cover. The definition of compact space tells that every open cover must have a finite subcover. And here we are having only one open cover, and that also having a finite subcover in the form of the cover itself. So indiscrete topological space is a compact space. So move on to the next very easy result. I have told you earlier that all the results we are going to prove today are very easy and are conceptual, which will make your base clear about the compact spaces. The next one is, prove that cofinite topological space is always compact. So earlier we have shown that indiscrete topological space is compact, and now we are going to show that cofinite topological space is also compact. So I am starting the proof. Let X top be cofinite topological space. So that means this top, the topology on X, it contains the sets, either the set in the top it is phi, or otherwise it is X, or if some other sets are there, then their complements must be finite. So to prove that it is a compact space, what I will have to do, I will have to take one open cover and I will have to find some finite subcover of that. So let C containing Gi, where I belonging to a particular family lambda, be an open cover, of this space X. Now take one particular member of this cover. So let G1 be a particular member of C. Now G1 is a member of open cover. That means G1 is a open set. G1 is an open set. And if it is an open set, it must be a member of top. And if it is a member of top, then its complement must be finite. So this means G1 complement is finite. Also, you can write your X as G1 union G1 complement. And G1 complement is finite. So you can write G1 complement as a finite set. Suppose it is the set X1, X2, X3 and Xn. Since each of these xi's belong to X, and C is an open cover of X. That means X can be expressed as union of Gi's I belonging to that particular family lambda. So what it means? It means that each of these xi's belong to some particular Gi. Xi belongs to union. That means Xi must be in at least one Gi. So take the smallest index I1 such that X1 belongs to Gi1, X2 belongs to Gi2, X3 belongs to Gi3. Ij is the smallest suffix such that Xj belongs to Gij. So let Ij be the let J be the smallest suffix such that your this element xi belongs to some particular set Gij. You take here xj belongs to this. For all j to be equal to 1, 2, 3 up to n. 1, 2, 3 up to n. That means your x1 belongs to Gi1, your x2 belongs to Gi2, your x3 belongs to Gi3, and so on. Your xn belongs to Gin. Consider this collection now. Consider the collection. I'm naming it as C star, and here I'm using one set G1 and rest of the sets I'm taking from here. So it is containing Gi1, Gi2, Gi3 and so on, Gin. This G1 is a member of C, and each of these Gij's is also a member of C. So that means this collection is a subset of C, because each of the members of C star is coming from C. So C star is a sub collection of C. Also, your X, I have written here, it is, I have written X here, and have a concentration here now. G1 is contained in G1, this X1 is contained in Gi1, this X2 is contained in Gi2, this X3 is contained in Gi3, this Xn is contained in Gin. That means whole of this union G1 as well as each of these elements is contained in these sets. So that means X is contained in the union of these sets. So you can say X is equal to union of G1 first, G1 union with union of these Gij's, where J is varying from 1 to n. So that means this is also an open cover, and since it contains finite number of members, so it is a finite cover. And since it is a sub collection of C, so you can say that C star is a finite subcover of C. So therefore C star forms a finite subcover of C. So what you have proved? You have taken an arbitrary open cover C of X and you have obtained a finite subcover of that cover C. So it means every open cover of X has a finite subcover, and that is the definition of compact space. So therefore your X must be compact. So it means cofinite topological space is always compact. So we have proved this result, and after proving this result, another easy result I am going to prove now, that the next result or theorem, whatever you want to say, you can say this is compact subset of a topological space need not be closed. In a previous video, we have shown that compact subset of a Hausdorff topological space is closed. But if you drop the condition of T2-ness, Hausdorffness, then the compact subset of topological space need not be closed. So we'll have to give an example, definitely. So I'm giving here an example. So in the proof, I'm giving an example of a compact space, of a topological space in which there will be a compact subset which will not be closed. So let your X be the set A, B, C, D. Let your tau be the topology phi. I'm having the topology here with me. Phi singleton set A, singleton set C, the set containing AD, the set containing BC, the set containing ABC, and the set containing BCD. And obviously there will be all of the set X. So it is a topology on X. You can check all the four properties of topology are being satisfied, so it is a topology. And now I will show that there will be a compact subset which will not be closed. So let A be the set containing the points A, C and D. Now whatever the open cover you will take for this set A, the largest open cover, which is the largest open cover? Let us discuss the largest open cover for this set A. This is, you will have this set A, you will have this set D. The largest open cover I am talking about, AD will be there, AD will be there, then BC will not be there. You can take BC, but no need to have it. ABC, no need to have it. BCD, you will have to take at least one of these, so let it be BC. So this is an open cover. You can take BCD also, you can take ABC also, you can take X also, but I have taken the concerned open sets only. So this is an open cover of A, because A is covered, because C is covered, because D is covered. And even if you delete these two, still it is an open cover, and in fact it will be a subcover also. If you consider the previous cover, then it will become a subcover, and it is finite because it is containing only two members. So whatever the cover you are taking of this set A, open cover, you will have this finite subcover. So that means this set A is compact. So this is a compact subset. This is a compact subset of X, because every open cover of A is having a finite subcover in the shape of C. Now this is not closed. Why? Because the complement of A is having only one element B, and this is not an open set here. If A is to be closed, then A complement must be open, but A complement is not open because A complement, that means the singleton set B, does not belong to your topology, so it is not an open set. So that means A is not closed. So there is a compact subset of X which is not closed, and it proves that compact subset of a topological space need not be closed. So the condition that the topological space must be housed off cannot be dropped. So another easy example I am going to take. So you can write question now. Question: prove that the closed interval 0, 1 along with usual topology defined on it is not compact. Before going on to solution, let me remind you the definition of compactness once again. A set or a space is compact if and only if every open cover has a finite subcover. So if I want to prove that it is not compact, what I'll have to do? I'll have to find an open cover which has no finite subcover. If I can find an open cover having no finite subcover, it will be proved that the space is not compact. So look at, you can have this type of intervals 0 closed to n upon n plus 1 open. So consider the collection of all such intervals. So this is an open cover. Because in the relative topology, the sets of this type closed from this side and open on the other side, or open on one side and closed on the other side, this type of sets in the relative topology of 0, 1 with reference to the usual topology of real numbers, these are the open sets. So this is a collection of open sets, and if you union all these sets 0 to n upon n, n upon n plus 1, where n belong to n, the union of all these is closed interval 0, 1. So this is there. Now this is an open cover because it contains all open sets and their union covers the closed interval 0, 1. But it has no finite subcover, because if it is having finite subcover, suppose a finite subcover C star is there. So since C star is finite, it will have finite number of members. So suppose the finite number of members be 0, n1 upon n1 plus 1, 0, n2 upon n2 plus 1, and so on, 0, nk upon nk plus 1. These are the open sets, or you can say these are a finite number of members taken from C. If it is an open cover, or you can say if it is a finite subcover of C, then it must cover the closed interval 0, 1, which is not the case. Why? Because when you will union all these, union of A, where A belongs to C star, that means I want to take union of all these sets, and union of all these sets will be 0 to m upon m plus 1, where what is m? M is the maximum of n1, n2, nk. Maximum of these all, if it is m, then their union will be 0 to m upon m plus 1. And very interestingly, you can note that m plus 1 upon m plus 2 does not belong to this union 0, m upon m plus 1. This element does not belong to this. So this element is not belonging to this, and this is union, this is the union, then how this union can cover 0, 1? Because this element is in closed interval 0, 1. So here is an element of the closed interval 0, 1 which is not covered by the union of all members of this subcover. So that means it is not a finite subcover. In fact, it is not a cover. It is only a collection of finite number of members of C, but it is not a cover. So that means there is an open cover which has no finite subcover. And if there is an open cover having no finite subcover for some space X, here the space is closed interval 0, 1 with usual topology, then this space cannot be compact. So we have shown that the closed interval 0, 1 considered as usual topology, relativistic topology to the topology on real numbers, then it is not compact. On the same lines, you can show that R with usual topology is not compact. Once again, why? Because consider this collection of the intervals of the type minus n to n, where n belongs to n. Now, what types of intervals will be there? Minus 1 to 1, minus 2 to 2, minus 3 to 3, minus 4 to 4, and so on. And their union, because n has no limit here, so the union will cover all the set of all the real numbers. So it will form a open cover, because each of the members is open set and it is covering your R. So it is an open cover of R. But once again, it has no finite subcover, because if some finite subcollection of it, suppose minus n1, n1, minus n2, n2, and so on, minus nk, nk. If it is a finite subcollection of members of C, then what will be the union? Union of A, where A belong to C star. That means union of all the members of C star will be open interval minus m to m, where once again m will be maximum of all these n1, n2, and so on, nk. But this union does not contain the element m plus 1. M plus 1 is not contained in this union, whereas m plus 1 is also a real number. So there are infinitely many real numbers, in fact, which are not contained in union of these finite number of members of C star. So this means C star is only a finite subcollection, but it is not a finite subcover of C. So once again, there is an open cover which has no finite subcover. That means this topological space is also not compact. So you have proved that the set of real numbers with usual topology is not compact. So one more example. There is a question. You can say, show that an infinite discrete space is never compact. And the proof is once again very easy. So what we are taking, X, an infinite set, and discrete topology on it. Let XD be discrete topological space with X as an infinite set. So I have taken an infinite set and I have defined discrete topology on it. Now what I need to show that it is not compact, I need an open cover having no finite subcover. So in discrete topology, you know that singleton sets are open as well as closed also. So what I am going to take, the collection of all singleton sets where X belongs to X, and the collection, then this is the collection C, and this is an open cover of X. Why? Because for every member small x of capital X you are having singleton set X, and when you take union of all such open sets, that means union of all the possible singleton sets, definitely the whole of the space X will be covered, because you are taking each and every element of the space X and then singleton set, and when you will union them, the whole X will be covered. So C is an open cover of X. So C is an open cover of X, but it has no finite subcover, because if you have some finite subcollection, suppose you are having x1, x2, xk, if you are considering this subcollection to be a finite subcover of C, then there will be a problem. What the problem will be? If you are saying that C star is a finite subcover, that means you are saying that the members of C star, they are covering X. That means X is union of A, where A belongs to C star. So that means you are saying that your X is union of all these members, and union of all these members is x1, x2 and so on, xk. So this is a big contradiction, because it is a finite set containing k elements, and you are saying that it is equal to X, where X is your infinite set. So an infinite set is equal to a finite set is never possible. So we are arriving at a contradiction. And why this contradiction? Because we have supposed that C star is a finite subcover of C. So that means there will be no finite subcover of C. So there is an open cover having no finite subcover, which makes that infinite discrete topological space to be not compact. So we have shown that infinite discrete topological space is never compact, and in the light of this theorem, you can very easily say that R, the set of real numbers with discrete topology, is not compact, because this R is an infinite set, and just now you have shown that infinite set with discrete topology is not compact. So how RD can be compact? So real numbers, the set of real numbers with discrete topology is also not compact. And one more example I'm going to give. So this is the last question, you can say, of this video. Give an example of a compact T2 space which is not connected. So in this question, I have considered the three concepts: separation axioms, compactness and connectedness. So they are not related to each other. If a space is compact as well as T2, it need not be connected. It may be disconnected. So we have to give an example of a compact T2 space which is not connected, and the example is once again very easy. So what you have to do, just consider the set X with 3 points ABC, and you take discrete topology on it. That means phi, singleton set A, singleton set B, singleton set C, the set containing the elements A and B, the elements B and C, the elements A and C, and obviously the whole set X. Now, your X is a finite set. Topology also containing finite number of members. If your topology is containing finite number of members, that means every open cover itself will be finite. And if the open cover itself is finite, you can say it is a finite subcover of itself. That means the space is compact. So one thing is okay, it is compact. Secondly, house law. If you take two elements, suppose A and B, then what you require? You require to prove it that it is a T2 space, two disjoint open sets containing them. So very easy. singleton set A, singleton set B. It belongs to, A belongs to this set, B belongs to this set, and their intersection is phi. So for every two elements, you are having their corresponding singleton sets such that the element belong to the sets and their intersection is phi. And these are open sets because they belong to your topology. So it is a T2 space also. So this is also proved. Now what else is required to prove that this topological space is not connected? If you remember the chapter of connectedness, there you have studied that a space is connected if and only if there exists a set which is not clopen, that means open and closed as well. If in a topology there does not exist a set which is open as well as closed, then it is disconnected. So here also this set is open as well as closed because its complement is open. This set is open as well as closed because its complement is open. This set is open as well as closed because its complement is open, and so on. So all the members of this topology are open as well as closed. That means there is not a set, there does not exist a set which is not clopen. So that means this topological space is disconnected, it is not connected. So you have shown that it is not connected. So this is the example of a compact T2 space which is not connected. So here I am going to stop this video. In the next videos we will have more and more theorems on compactness. Thank you once again.